now it's time to talk about voltage. This is a super important concept. It's just as fundamental as current, although not as physical. It should be super easy to understand, and a lot of people do or think they do, but there's a lot of common misconceptions about it, or just simple misunderstandings, and they're gotchas for sure, but you should be aware of them. So let me step through this slowly, and let's get into it. All right, now if I had to define this in one sentence, what would I say to start things off? Well, the easiest way to think about it is just this. It's a potential energy density. And already, this is where most people get lost. A lot of people think voltage is potential energy. It's not. It's close to that, but not. Voltage is a potential energy density. And that density part is really important. A lot of people leave that off. A lot of people aren't even aware of what this really means, and they just think of it as potential energy. And this will get you 90% of the way. I guess if you don't understand something, you can still apply it a lot of times. But if you really want to understand this, you have to remember this part. The units of voltage, to build on that short definition, are joules per coulomb. If you don't know, a joule is the baseline unit of energy we use in engineering, and a coulomb, if you remember from the last video, is our baseline unit of charge. So what this really parallels is energy per charge, and that's so joules per coulomb, and that equals volts. So again, voltage, to write this out in words one more time, voltage is energy per unit charge. And so my tangent about the difference between potential energy and energy density should make itself very clear right here. This is a density. This is energy. This isn't energy. Voltage is not energy. It's energy per unit charge. This is a density of energy with respect to charge. Now think about for a second what that might mean in the context of a circuit. Because yeah, okay, current flows through a circuit, but what is current really? It's charge. Current is the time rate of charge. Okay, so if you have a current through a circuit, all of a sudden you're counting charges, and each of these charges has a certain amount of energy associated with it. So if you know how much energy you have per unit charge, and then all of a sudden you start counting charges, well then what can you do? All of a sudden you have energy, right? And so you're going to see where I'm going to go with this shortly with voltage and current and how they relate to each other. Well, something that you'll learn very quickly is that you will never see a current without an associated voltage, and vice versa. You will never see a voltage without an associated current. But what does this mean in the context of a circuit? I'm going to draw a familiar diagram here, or just kind of recap something that I explained in the last video. Now let's say you have this conductor or this tube, and then I catch this cross section here where there's a current flowing through. So there's some circuit element here, some conductor with current flowing through it. And we can sit here and count charges all day, right? But now for each charge that goes through, we might define, let's say the current starts here on the left and flows with the arrow to the right. We might define a voltage across this circuit element as current flows through it. And this is a fundamental thing that you'll carry with you going forward forever. Anything with current flowing through it will have a voltage associated with it. And this voltage polarity is associated with the current polarity in some way. So the fact that the current flows from one direction to the other, that current has a polarity. And you could assign it however you wanted. Remember what I talked about with AC. You know, if you're crossing the zero crossing of the current's changing direction, that's when we assign this positive or this negative sign. And the same is true with a voltage. The polarity of the voltage we assign to a current or a circuit element really just describes whether or not that element produces or consumes energy. So here's what we do. Let's define a voltage across this circuit element. like this. And this is how we do it. We use positive and negative symbols to describe voltages in our circuits. If this were a real circuit or a schematic diagram, we might have circuit elements drawn out with symbols that I haven't taught or explained yet, but what I would really do if I wanted to describe a voltage across it would be to draw these symbols, this plus and this minus sign. And usually in our circuit schematics, we don't draw these currents, right? Like it's usually we'll describe the voltages. We'll put voltage polarities around circuit elements, and then from there you infer the direction that the current flows. Because in many cases, depending on the circuit element, the voltage polarity that I draw across it gives you all the information you need to know about what direction that current's flowing, or at least with respect to these polarities. Usually, in a circuit, we won't draw the currents, we'll just draw the voltages. And as an engineer, you have the background to understand that depending on the circuit element, that voltage polarity gives you all the information you need to know about the direction that the current's flowing. So to sum this up in reference with my original definition, the voltage associated with the circuit element is the energy transferred per unit charge that flows through this element. Now to expand on what I just said, let me give one more example. So I've drawn a circuit element here, and let's say we have a current, and this is purely, this isn't physical at all. I'm just drawing these things. I'm just drawing these things so we can talk about them. If you have a circuit element and you have a current, what voltage really describes is the energy per unit charge that's exchanged between these two. So either the current will deliver some amount of energy per unit charge to this circuit element, or the circuit element will deliver, now let's say this is I of t, and this is a circuit element, or the circuit element itself will deliver some amount of energy per unit charge that flows through it from this current. So really what you have is you have circuit elements and you have currents, and the voltages across those elements, or the voltages associated with those currents, just describe the transfer of energy. And now which direction that energy is transferred, either from the current to the element or from the element to the current, is dependent upon the polarity of the voltage relative to the polarity of the current. And now I know that sounds really vague and semantic, and it sort of is and sort of isn't, but I'll explain more about what I mean as I talk about power and energy. Let me just write that there. Let me talk a little bit about the car battery for a second. So imagine you have this scenario where you have a car battery, and it has these two terminals with wires attached to it that go off to someplace in the car, connect to a bunch of stuff, and then the wires come back and connect to the battery. So if you've ever looked at a car battery, you might have noticed it has a polarity. There's symbols on the battery. You might see a plus and a minus terminal, and that's describing the polarity of its voltage. So there's a voltage between these two terminals here, and for a car battery it might be 12 volts, let's say. And there's some current that flows while this battery is driving your car. Now this is very important. While it's driving your car, its current flows in this direction. It flows out of the positive terminal. Now when this battery is connected to your car, it's sourcing current or energy, right? It's a voltage or a power source. It's a current source. And current leaves this battery, energizes the circuit elements in your car, and then it returns at lower energy. And so now this is where a lot of the concepts that I've talked about really start to come together, because if you remember, current never just flows in one direction. It's always flowing in a loop or a closed path or a circuit, right? Current flows through circuits or loops. So for every unit of charge that leaves here, well, some comes back. And now with this is the same current. Not only will it be the same magnitude, it's literally the same current. This current is this current. There's only one, right? It flows in this loop and comes back to this battery. And where this gets really interesting, what the voltage tells us is the difference in energy between these two currents. And what that means, if you remember, volts is joules per coulomb. It means that for every unit charge that flows through this battery, i.e. every coulomb that flows through this battery transfers 1 joule of energy to that charge or to that current. So as this current comes back de-energized, the battery's going to give it back another joule per coulomb, or in this case 12 joules per coulomb. 12 volts is 12 joules per coulomb. If this was a 16 volt battery, it would be 16 joules per coulomb. And so the higher voltage you have, the higher transfer of energy you have from this source, let's say, to this current, or it could be from the current to the source. What happens when you have a battery, let's say it's the battery in your phone, and at night it's time to go to bed, time to plug this thing in? Well, what you do is you plug it into the wall socket. Say it's this guy right here. Got a plug on there, and well, you wouldn't see this. Ignore my horrible drawing for a second. Just imagine you have another battery. Let's say it's your phone battery, and you plug this thing into the wall socket at night when it's time to go to bed. In this case, the current from the wall is flowing into the positive terminal of your battery, of some voltage battery. And that's really interesting, because what that means is that this current coming from the wall is delivering energy to your battery. Because given our reference polarities and the reference polarity of the direction of current flow, this is how we describe accepting energy. So in this case, this voltage is sourcing energy. In this case, it's receiving energy. This battery is being recharged, and the rate at which it's recharged, or the transfer of energy from this current into the battery rather than out of the battery, is still described by its voltage. So in this case, if this was a 1.8 volt battery, that might mean that the joules per coulomb, the energy density that's transferred from the wall, from this current into this battery, is the same as when this battery was sourcing current. So in the case of the car battery, when you jump your car, the energy transferred from that current to this battery is still 12 volts. The difference is the battery sourcing or consuming the current? And actually, that's a poor choice of words. It's not consuming, it's accepting and storing the energy. What consumes current or energy is all this stuff out here that's being loaded by the battery. And so I think where a lot of people get lost is the difference in physicality between a current and a voltage. Is a voltage really a physical thing? I mean, it definitely describes a physical relationship, but our voltage is real, right? Like, it's the same concept of is energy real? You know, it's energy as an idea is something that we use to describe physical phenomenon in our universe. And so I think a lot of people would say, yes, energy is real, but think about the way that we describe potential energy in physics, right? In physical systems and in physical analysis, right? Like if you hold a ball at the top of a hill, you say it has potential energy. But what does that mean? Is that a physical thing? I mean, not really, not in any human sense, right? Like physically we say like this thing has the potential to roll down the hill if I let go of it. But it's not like it's about to explode because it's hot. I think the question then is potential energy real? And depending on who you ask, whether or not it's a mathematical or a philosophical discussion, I think you might get a different answer. And I think when it comes to understanding voltage, people get lost because it seems like it's kind of you're chasing your tail when you try and understand what it is. And I think what you need to realize is that this is something that we've invented to describe physical phenomenon. Like most concepts in math, science, and engineering, We invent ways to describe things. So what voltage describes is this transfer of energy between current and a circuit element, right? Current is a very physical thing, and even current, like I said before, isn't the most fundamental process at play here. There's charge moving around in these circuits, and charge is fundamental, right? And those charges have kinetic or active or electrical energy, right? And that is a physical thing. That's easy to understand. But potential energy, or the ability of that charge or that current in its interaction with a circuit element or vice versa to exchange energy, now that is something that's hard to wrap your head around. And I think where people get lost is if you look at a real circuit and you say, oh, there's some voltage here, this battery has a voltage. Well, I mean, that voltage isn't so much a physical thing as its chemical makeup, right? Like, we've just looked at this battery's ability to exchange energy with current that flows through it. And based on that ratio of joules to coulomb, well, we say, oh, it's 12 joules to coulomb, so we're just going to say this battery is 12 volts. And so I just want you to think about it in that way. You know, like, this is something that we'll wrestle with all the time. You know, what truly is, there's a cause and effect relationship here, and which is the cause and which is the effect. Do voltages cause currents? Do currents cause voltages? What's really more fundamental, or what's the real starting point? And I know a lot of this can get confusing, but just think about what I've said about how we use these ideas to describe things. And I wouldn't get too lost in trying to understand some deep meaning for voltage, because it's really not that deep. You know, it's something that, it's just a way we describe certain processes in our circuits. Okay, I've talked about voltage, current, and energy, and now I'm going to talk about power. So and this is just a very simple corollary of what I've already discussed, so let me just write some things out, just so we recall. Current is coulombs per second, and voltage is joules per coulomb. So if I was to take a product, and this might seem random, but if I was to take a mathematical product of current times voltage, think about what I would get with these units. What I really have here is charge per unit time multiplied by energy per unit charge. And now if you just watch where this goes, what you have is energy per unit time. In other words, power, or watts. And now this is something totally classical that you'll see in every electrical engineering textbook. This is a concept that you'll carry with you until the day you die. It's super important. But a lot of times people just forget the physical phenomenon at play here, and it's just a super simple product of current and voltage. And if you remember these physical phenomenon, what's happening, like you literally just have some time rate of charge, and you have some ratio of energy to unit charge. It really is that easy. This is just energy per second, and that's just the definition of power. It's a rate of flow of energy, or a rate of exchange of energy. And so when someone says, oh, what's the power of that load, or what's the power in that load, or what's the power of that source, or what's the power delivered to that element, what power really means is it's the time rate of energy. It's how fast energy is delivered or sourced from a circuit element. Okay, for the sake of an example, I've drawn a vague but complete circuit here. And now I haven't discussed these properties of circuits about how voltages behave. And I will get to this, but for the sake of the example, just bear with me. So this circuit element is passive. This is a source, and this is passive. So there's this current flowing out of this battery into this circuit element. And the voltages where these elements are connected, so the source is connected via conductor to this element by these two lines I've drawn here, which represent wires. And so their voltages are the same. One of the things you'll learn about conductors is that there's no voltage across them. So any two things connected by conductors share the same voltage. So there's this 12 volts being sourced by the battery, and it appears across this load. And now there's a current, and now there's a current flowing from this battery into this load. And so the question is, I mean, we all know this is a battery, right? This is sourcing energy, this is sourcing current, this is sourcing power. And this passive element, the current's flowing into it. So this is consuming the energy, consuming the power. And so by definition, we usually say that when we talk about power consumption, that's a positive power. And we usually say that when we're talking about the source of energy or power, that's a negative energy or negative power. And where that makes itself clear is how we assign reference polarities for voltages and currents. So if that's the case, for this IV product to make sense, we have this voltage that's positive as we go from this plus to this minus terminal across this load. And the current here is flowing from the positive to the negative polarity. And in that case, we call that current positive. And so if that's the case, the power consumed by this load, well, this gives you a positive number because we've defined this to be a positive current, and this voltage is positive as you look from this terminal to this terminal. So then we say, okay, that product is positive, and this is a positive power being consumed by this load. But in the case of the battery, the current leaves the positive terminal rather than entering it. And so in that case, based on how we've defined our reference polarities, we would call that current negative, which with a positive 12 volts, that product would give you a negative power product, which just so happens to equal the power product in this load. And so that's our cute conventional way of saying, oh, this is a source and this is a load, because based on how we define our current polarities, you get a negative power from this battery, which means it's a source, and you get a positive power consumed in this load, which means it's passively consuming. And so that's just a little taste, a little flavor of a lot more detail that we'll get in down the road later on. But I'm skipping over a lot of things, I'm rushing through a lot of things here, but I just want to give you a little taste of what we really do, or I just want to give you a little taste of how we think about things and what's coming. Okay, I know that's a lot of concepts to cover in this video, and I am being very superficial and glossing over a lot of things, so I think this might be a good time to stop. But I think hopefully what I've done here is just give a nice overview of a lot of the terminology and concepts that I'm going to talk about going forward as I get into more rigorous detail. I think the next video I might do a little bit of real analysis or some sort of algebra, something like that. I'm about to introduce some important concepts that you really need to have grasped the difference between voltage and current and power and energy to understand. And I hope that I'll tie up a lot of the things that I've talked about the last two videos really going forward. I mean really it'll take your entire education to tie these things in a nice knot and say you understand them. So forgive me for being vague or brief, or maybe hand wavy in a lot of cases here, but I promise we will do a better job. So I hope this was helpful. So get excited for the next video. It's going to be the most important one so far, and I think I'm going to continue to say that with each video. As we keep building, each one becomes more important than the next. So let's do it. I think next time I'm going to talk about Kirchhoff's voltage and current laws. So get ready for that. And I hope this was helpful. I hope you enjoyed. Thanks.